All right, let's get started from current slide. I did see a few announcements over the weekend as I was able to go through some old emails and stuff. And I thought I would have time this morning to print some of them out, but I had to do some stuff with Human Resources Office, and I had to do something with work study program and my work study student. And I also had to answer a bunch of other emails that came in since then, and suddenly all the time was gone. So I didn't get to print those off. I will have sometime this afternoon, possibly, supposed to have 3:45 until 6 available. Hopefully I can get some of the those announcements printed. So, sorry. So I can make those in class. I had tried not to get one of these in my mouth while I'm trying to teach, but I don't think I'm going to be able to avoid the possibility. So, excuse me. These aren't quite cough drops, but they're as effective. It's a ginger candy from Indonesia that's really strong with ginger, and it really seems to help my throat. Hopefully my cough. Okay. Any questions on anything we've done so far? I'm trying to hear. So what? Okay, you have a bunch of videos? That's what? Oh, I see. Well, if you could watch those, if you have questions, please ask. Okay. Let me mark you here, too. Okay. Have you had the cold? It seems to be going around. I hope I didn't give it to you. But it's not good. Okay. Before we get started where we left off before, well, it's part of that, but we're now in 9.2. We've only got a couple pages left in 9.2. And then we're not going to do any more with 9.3 and so on. I may just do a quick PowerPoint show, but you're only responsible test-wise for 9.1 and 9.2. So we'll do a quick, hopefully quick, PowerPoint show on 9.3, 9.4, and 9.5. 9.6. There's a lot in here, but we just don't have time for it. The course description only called for, hey, howdy. Here's Tiara. Only called for sequences and series, and when we finish 9.2, we'll finish that. But like I said, I'll try to do a quickly as I can, slideshow on the rest of them, 9.6, 9.7. Now 9.7, we won't go over, but it's a pretty important, and we'll talk about it when we get there. Without knowing it, you've probably used this a lot. And then power series, again, quick PowerPoint show on this. I'll say quick. I hope it'll be quick. And 9.9, geometric power series, we'll do that as quickly as possible. 9.10 is in the Taylor and McLaurin series, as opposed to 9. 7, I believe it was, which is Taylor polynomials. It's using Taylor polynomials as an infinite series. Why you split them up this way, I'm not sure. Okay? And it's actually the Taylor series you probably have used without even realizing it. That does finish the chapter, but there's not a test then. What we're going to do is move on to chapter 10 and get as much of 10 covered as possible. We're going to skip 10.1, start in 10.2, 10.3, and 10.4. And we'll do those three sections. I'll do slideshows on the rest of them. 10.1, 10.5, and I think 10.6. Okay? And then when we finish those in 10, we'll cover as much as we can in 11. Okay, that's a lot. Sounds like a lot, but that you're responsible for is only 9.1 and 9.2, 10.2, 3, and 4, and then what we get covered in 11. We have class this week. I guess y'all know the bad news, don't you? Y'all are off next week, completely. We have meetings, okay, Monday, Tuesday, and Wednesday, but the college is closed Thursday and Friday for Thanksgiving. But y'all don't have to be here the whole week. So the college will be open. So if you have any business to take care of at the college, you can get that done Monday and Tuesday of next week. And Wednesday morning. But I would not bring any important business in Wednesday afternoon because you may find offices closing up early. They typically do give us, they aren't required to, but typically, historically, have usually given, let people go early on the Wednesday, the day before Thanksgiving. So I would not bring any business to the college Wednesday afternoon and expect to get it done. You might be able to find someone in an office, but then you might not. So if you have business to take care of, do it Monday, Tuesday, or Wednesday morning. Then we come back from Thanksgiving, have one more week of class, and then we have final exams. So the last day of class, I will give you the test on whatever we've covered up till then in chapters 9, 10, and 11. And that you'll have then till the next week to get it turned in. Okay. Now, while I'm talking about that, I've received just one research paper in. Hey, you only got a couple more weeks, to get those in. Test 1. 1, 2, 3, 4 people haven't turned that in. Only 5 have. Test 2, 0 have turned it in so far. So please get test 2 completed, especially before it's time to do test 3, the last exam. That's putting way too much at the end of the term. Okay, any questions? Anything we've covered so far? All right, and again, I apologize for my voice. I'm hoping I'm on the downhill side of the cold, but the voice hasn't come back too well yet. Periodically, the cough comes back pretty badly. And I've got something in my mouth now to help with the cough, so if I sound sort of mealy-mouthed, that's why. All right, we've been talking about series. Now, I know that neither one of you were here last time, and I can't remember exactly when we started. But a sequence is a set of numbers, generally with some type of pattern, okay? Just a set of numbers. What a series is the sum of a sequence, okay? You're adding those numbers together. So with series, you will see the summation sign. And these are infinite series, so they go on and on and on and on and on. You might say, how can I add a series of numbers together if there's no end to them? Okay? It seems as if they would just keep getting bigger, bigger, and bigger. Well, if the numbers are getting sufficiently small, it could be there's some limit out there and they'll never reach it, but they're approaching it. And that's what we're dealing with. Okay? So, how we deal with it is, okay, remember, we started with a set of numbers, and generally they were infinite as well. You know, they go on and on and on. When you add those together, that gives you a series, okay? Well, then what you do to evaluate this is look at what they call the partial sums, okay? Say when n is equal 1, you know what value that is. When you do n equal 1 plus n equal 2, you know, for that expression, that gives you the next one. And then again, and again, and again. So each one of those is called a partial sum. Well, that recreates a new sequence of numbers. Now, they're related to each other in a little more complicated fashion, but they are related. So, you start with a sequence, you add them together to make a series, and then you evaluate the series by looking at the sequence of their partial sums. Okay, so here are some of the properties of an infinite series. If the summation of a sub n and the summation of b sub n both converge, that means there is some finite limit out there that even though the numbers keep adding, you approach it but never reach it. Okay? These are convergent series. Let A and B, capital A, capital B, and C be any real numbers. Not any real numbers, they are just real numbers. If the summation of a sub n, little a sub n, is at capital A, and the summation of b sub n is at capital B, like I said, these convergent series, these are the values they converge to, then the following series converge to the indicated sums. I'm sorry about the board. Whoever was in here last left some marks on the board. When I went to erase them, it smeared all over the place. Okay.
Why you middle, sorry to interrupt, but why you in the middle of the sentence?
Yeah.
Because I want to request more of these. I mean, we have a massive board work today, so.
Okay, do you need them right now? Huh? Do you need them right now?
Yeah.
I've got one right now. I found in the drawer here. I don't know how old it is, but the last time I used it, it wrote, so.
Yeah, I started
you need more?
myself to it. Yeah.
Okay, well, then let me.
You get a break.
Well, it's going to be a while before I have a break. We just got started. So let me pause this and go. All right. Sorry. Next door, they had run out of markers. I went down to my office to get them and found an ID in the hallway and tried to find a student was in one of the classes down there to whom it might belong. He wasn't in the first class, but he was in the next one, but I had left it with the first instructor because she said it might be the class after theirs, you know, hers. So anyway, I finally got them reconnected. All right, so here's your deal. If you have two series, A sub n, B sub n, are both convergent series. That means there is some number out there that the sum of those, all this infinite sum of numbers is approaching, never reaching, but approaching some value. Okay? And A, capital A, is the value of the limit of the summation of little a sub n. Capital B is the limit of the summation of little b sub n. Then the following series also converge to the sums they indicate. Here's the first. The summation from n equal 1 to infinity. Sorry. That's usually the way they do these sums 1 to infinity. They don't have to. They could be from 0 to infinity. Usually don't happen, but they could actually be from a negative number to infinity. They always have to be integers. Most of the time positive integers. Most of the time 1. But the summation of C times A sub n. Now C can be as big a number as you want it, but it has to be a finite real number. So even if it's an enormous number, if you multiply that big number by this sequence, okay, each value of the sequence, sum those up, you still come up with a convergent series, and that series will just, the sum of that will be C times that value that you had for A. Okay? That's the scalar multiple rule, you might say. Number two, if you have a summation for n equal 1 to infinity, of adding these two infinite series together, term by term, by term, by term, by term, and adding them together. If one of these goes to A, the other goes to B, then sure enough, the sum of that sum series is A plus B, and the third one is the difference of those would be A minus B. Now, capital A minus capital B. Hopefully you look at these and say, oh yeah, that looks like that would make sense. And indeed it does. These are, this is a scalar multiple, this is the sum of series. And both of those work. And in another life, you may learn to call this then a linear system, so to speak, because these are the two primary features of operations that are linear in nature. All right. Let's come now to the nth term test for divergence. We've been talking about and trying to find series that converge. Now we're going to look at the limit of an nth term test for divergence. Here are two theorems here, the first of which, center of page 603. If the summation of n equal 1 to infinity of a sub n does converge, then the limit as n approaches infinity of a sub n, that's the sequence a sub n, it has to be going to 0. Okay? No question about it. Now, remember we did sequences in the last section. The sequences could converge to other things. If they converge to anything other than 0, there's no hope for the series made up of those terms, the summation of those terms, to ever converge. The limit for the sequence must be going to 0. Because if it's not, if it's going to any other number, even if it's a small number, negative number, whatever, if the sequence is going that way, then there's always another value you're adding to it, positive or negative, and that keeps going to get bigger or smaller. It can't possibly converge. Okay? Now, the contrapositive of this theorem, meaning if this were true, does that mean it converges? Okay? Provides a useful test for divergence. Okay? This is the nth term test for divergence. It states that if the limit of the nth term, which we're talking about here, of a series does not converge to 0, now that's actually saying a sequence, I don't know if they just got the word wrong or not, does not converge to series, then the series must diverge. Okay? So, I didn't quite say it right, the contrapositive. If this is true, we're not saying anything about if this is true, does this always happen? Not going to go there yet, okay? My inclination would be no. But if this is not true, if this is not going to 0, there's no way this can converge. So that's your test for divergence, and that's what we list here. If the limit, as n approaches infinity, of the sequence a sub n does not approach 0, no matter what it's approaching, small numbers, big numbers, it doesn't matter, then there's no way that series could converge, so it has to diverge. Okay, so it wasn't quite what I said earlier. If this is not 0, then this has to diverge. That's truly what they mean by contrapositive. If you turn them around but make the first one false, that makes what was your first one, now your second one, the opposite as well. All right. So here we have a series. Okay. Is there any doubt in your mind that the summation is n equal, this one there's beginning at 0 and going to infinity, of 2 to the n? Is there any doubt in your mind that's going to explode on you very quickly? If n's equal to 0, that's just 1. If n's equal to 1, that's 1 plus 2, 3. It's increasing now, isn't it? Then, when n is equal to 2, that would be 1 plus 2 plus 4. 1 plus 2 plus 4 plus 8. 1 plus 4 plus 2 plus 16. 8. Those are exploding very, very rapidly. And you're adding them together, they get even bigger. Well, obviously, the limit of the nth term, 2 to the n, as that goes to infinity, that's not even converging. It's exploding itself. So there's no way that the sum of that couldn't be exploding, because 2 to the n, like I said, if n is starting at 0, that would be 1, 2, 4, 8, 16, 32, 64, 128, just getting enormously bigger as you go. That's just a sequence. And if that's going to infinity, the sum of those numbers has to be going to infinity. There's just no question about it, and that's by that last theorem. So the limit to the nth term is not 0. The series diverges. You don't even have to start adding them together. No way. Okay. Now, how about that one? For the series summation of n equal 1 to infinity of this, n factorial over 2n factorial plus 1. Well, let's just take the nth term, okay? And as n it's going to infinity, pick any large number out there, then n factorial up here, the same n factorial down here, but multiplied by 2, and then add 1 to it. Well, that's certainly, that sequence is not divergent. It's convergent. And here's sort of the best way to do that. Let's divide numerator and denominator by n factorial. That's just a finite number, right? So this will be n factorial over n factorial. That's in the numerator. 2n factorial over n factorial plus 1 over n, I can't write, n factorial. That's ugly. Okay, everything disappeared. Goodness gracious. Pen's not reacting well. Okay, over n factorial. Well, this, hopefully you'll see, is going to 1. This one, n factorial over n factorial is 1. So you got 2 plus, and this n factorial getting big really fast, and the 1 over a huge number that's getting even huger is going closer and closer to 0. So that would be 0. So this limit is 1/2. Okay? So this converges. The sequence converges to 1/2. But that's not 0. So therefore this series, which looks like, because this thing's getting smaller, perhaps it could be. No way. If every term you're adding is something greater than 1/2, or even getting closer and closer to 1/2 to what your previous partial sum was, then that just keeps increasing and keeps increasing and keeps increasing without bound. So this has to diverge as well. And that's what the theorem tells us. So the nth term, since it's not 0, the series has to diverge. That's what that last theorem, 9.9, told us. All right, there is a C part. How about this one? For this series, the summation of n equal 1 to infinity of 1 over n. Here we have the limit as n approaches infinity of that last term, the nth term. This is going to 0. Does that mean this converges? It means if this converges, the last term has to go to 0. But notice it wasn't if and only if. It just said if this happens, that goes. For it to go both ways, they have to say if and only. Well, they don't have to. Usually you would say that. This does not guarantee convergence. Just because the nth term is going to 0, it may not be going to 0 fast enough. Now that's a really slimy way of saying it, a wiggle worm there. Weasel word is what I'm trying to say. I can't talk. Because the limit of the nth term is 0, the nth term test for divergence does not apply. You cannot draw a conclusion about convergence or divergence. If you know that the series converges, that means that nth term has to be going to 0. But it doesn't mean that if the nth term is going to 0, that guarantees convergence. It may, but it may not. But if that nth term is not going to 0, no matter what it's going to, no matter how big or how small, then it can't be, it has to be diverging. So you don't know. And in fact, what we'll see a little bit later is that one. In the next section, you will see that particular series diverges. It does not converge. They left off example 6, so let's go back and do example 6. A ball is dropped from a height of 6 feet. Okay? I wish they had drawn the graph. Do both of you have text? Do you have an e-text? No. Okay, well, let me go on and draw this. Okay? All right. These are your height in feet. Okay? 1, 2, 3, 4, 5, 6 feet. A ball is dropped from this height. Okay? 6 feet. And begins bouncing as shown in the figure. And I'm trying to draw that. Now, it's really bouncing up and down. But because that would get really hard to see after about the third or fourth bounce, if even that far, we're going to put a little bit of distance between them so you can see. Okay? The height of each bounce is 3/4 the height of the previous bounce. So this is going to come down here, hit the ground, and then bounce up. 3/4 of 6 is 4. Right? And then, actually these, if I remember right, they make these dashed lines. Okay? And then it comes down, and 3/4 of 4 is 3. So the next one bounces up to 3 and back down. And 3/4 of 3 is 9/4, right? So that would be 2 1/4. Okay, so that would bounce up to here. Okay, and 3/4 of 9/4 would be 20. Wait, I did that wrong. No, 3/4 of 9/4 would be 27/16, and that would be just a little bit more than almost 2. Okay, okay, and then 3/4 of that and 3/4 of that. So it's going up and down and up and down and up and down. Okay, now when the ball hits the ground for the first time, it's traveled 6 feet. Ignore the little bit of horizontal displacement that it looks like. It doesn't have a horizontal displacement. These are just your eyes here. It's just going up and down, but we're letting them spread out a little bit. Okay? After the second drop, it's 6 feet plus 4 feet, okay? But when it hits the ground again, it's the second 4 feet, okay? So when the ball hits the ground for the first time, it's traveled, and they're saying D1 is equal to 6 feet. It's down here. It's traveled 6 feet. Okay, D2, that's the, I guess what they're defining that to be, is the distance traveled up and down since the last drop. Well, that was a 3/4 and 3/4. So, I mean, a 4 and a 4. So that's equal to 6 times 3/4. I didn't say that right anyway, did I? Sorry about that. It's not 4. 9 halves. But on its way down, it does another 9 halves. Okay? So it's 2 of those. Okay? And drop 3, after it comes up here this time, no, it hits the ground here, it goes up and down, and it's 3/4 of where it was before. So that's, okay? So you see each drop is producing a geometric series, okay? Well, close to one anyway. That would be and you got 2 of them, so it would be another 6 times 3/4 times 3/4, which is going to be 12 times 3/4 squared. Okay? And if you keep doing this, okay, there's going to be a 12 in front every time, and the 3/4 is going to be a series. So here we have D sub I would want to call this N. They're not calling it N. They're just letting it be D, is equal to 6 from that first time plus, and this, by the way, is 6 times 3/4 squared. So don't evaluate it. It's just 6 times 3/4 squared. No. All right. Okay. Let's forget about evaluating altogether. So much easier. Just let the sequence take care of it for you. Drop 2 is going to be that down plus that up again. 6 times 3/4, which again is 12. Yuck, I can't add. I can't write. Okay. 12 times 3/4 to the first power. The next one to the second power, the next one to the third power, and so on. So when you add these together, let's do our first one because that's only one trip down. Then it's going to be plus 12 times the summation of 3/4 to the nth. And this will begin at n equal 2 to infinity. Oh. Yeah. They change the thing on you and make it n plus 1. Okay? So this will actually make it 0. Okay? All right. N equals 0 to infinity. Because the first one will be to the first. So that would be that one. And then the next would be squared. Okay. Well, now that is a close to a geometric series. To make it even closer, you do this. D is equal to 6 plus, now, you got the You got the 12 here. Pull out one of those 3/4. Okay? And then you're doing your series from n equals 0 to infinity of 3, I can't write, 3/4, because if you pull one out, now it's just n. Okay. All right. Well, 3/4 of 12 is 9. Okay. So this will be 15 plus the summation n equals 0 to infinity of 3/4 to the n. Well, that's a geometric series. And that geometric series, remember, was I'm sorry, I did that wrong. I forgot this is a coefficient. You can't add it. It's 6 plus 9. I thought it was 6 plus 9 plus. It's not. 6 plus 9 times that. So you can't add those two. It's just 6 plus. Now, your numerator is going to be well, you can factor out the 9. Leave it factored out. 9. And your what did they call it in the geometric series? Was that the C or the A? I can't remember how they... Yeah, A times R to the n. A is 1, okay, so you don't have to worry about that. And then this would be 1 over 1 minus 3/4, okay? You go back to your theorem 9.6 on page 601. You see it's A, which in our case is 1, times 1 minus your R. Your R here was the 3/4. So this will be 6 plus 9, okay, times 1 over 1/4, which would then be 6 plus 9 times 1 divided by 1/4 is 4. So this would be 6 plus 36 is 42. Okay. Strange number. Okay. Oh, yeah, I've already got you here. But that's how far the ball travels, because we started in feet and this will be in feet. It almost looks like it's going to be big enough that you think there's never going to be an end to it, but indeed there is, because that is a geometric series. Geometric series do converge. Of course, this number is going to make it a pretty good number. That multiplied by it's going to make it a pretty good number. So yeah, you get quite a few feet, but that's what that geometric series converges to. Rather strange kind of problem, but certainly one that's doable. Okay? That's it for section 9.2. Any questions on that? All right. Homework exercises here. Again, I apologize for my throat. I feel like it's getting worse and worse. Do any of the odds 5 through 9. They're all at calcchat.com. Then do any of the odds 11 through 17. They're all at CalcChat. 11's at CalcView. Goodness. Do any of the odds 19 to 23. They're all at Calc. Sorry, CalcChat. 19's at CalcView. Do either 25 or 27, both at CalcChat. Any of the odds 29 to 37, all at CalcChat. 33's at CalcView. Any of the odds 39 to 43, they're all at CalcChat. Any of the odds 45 to 57, they're all at CalcChat. 47's at CalcView. 59's an exploring concept. You can try that if you'd like. I assume the answer or some explanation will be given at CalcChat. I don't know that for sure. I can't breathe. Do any of the odds 61 to 65, they're all at CalcChat. Now what they're saying there is find the values of x that will make those series converge. Okay, sort of doing in reverse what we've just been doing. All right. 67 should be a calc chat. 69 should be a calc chat. And then of the applied problems, any of the odds 71 through 75 should be a calc chat. There's a probability problem, 77, it should be a calc chat. And another 79 should be a calc chat. So should 81. 85, 3 or 85 should both be a calc chat. 87 or 89 should be a calc chat. 91 through 95 are true false. They should be a calc chat. Sorry. And then 97, goodness gracious, should be a calc chat. There's Fibonacci series we talked about last time is a calc chat 99. 101 is a proof. You can do that if you like. It should be a calc chat as well. There is a blurb there, gives you a reference for convergence with pictures like they showed in 102. You don't have to do 102, but if you want to follow up on that, you might find that a potential paper topic. Putnam challenges are usually pretty tough, so it's only at your choice. And then this Cantor's disappearing table is kind of an interesting I don't know what to call it, theoretical application or something like that. And you can see they give you a citation for that as well. Now, before we get going on 9.3, which we're just going to do PowerPoint show, I need to go to the restroom and clear my head again. I'm having harder and harder time breathing. And for those who came in a little late, the rest of this chapter, chapter 9, you're not responsible for on the test, but I did want to just do a quick PowerPoint of it so you can see it, be exposed to it. If you ever need it, you'll know where to go back and find the information. So before we get there, let me run down. I'm having such trouble badly as I have, period. So let's go from current slide. Now, again, this is just going to be PowerPoint, so you can be exposed to this stuff. We're not going to do the examples like we normally do. Well, I'll talk through the ones they show, but not do them individually. 9.3 is the integral test and the P-series, okay? Now, if this is beginning to sound a little bit like the geometric series, it's not. It's not the same thing, but it is something, one of the other series that we look at. And if you remember back, the next to the last example, that the nth term converged to 0, but the series, they said you can't tell, but in notes said later, next section, you'll find that that's what P-series will tell us. That one would not converge. So we use the integral test to determine whether an infinite series converges or diverges, and then we'll use properties of P-series and harmonic series, a really good physics word. You run into that all the time in physics. So let's start with the integral test. Here is the theorem, or the definition theorem that describes the integral test. If f is a positive, no, that means never goes negative. It's always going to be above the x-axis. Somewhere in the first quadrant, always. Continuous, no discontinuities there. And decreasing function for x greater than or equal to 1. So between 0 and 1, it could be anywhere it wanted to be, but after 1, from there on out, it's going to be between 0 and 1. Okay? So it's going to be, and it's going to be decreasing for anything for x greater than or equal to 1. Okay? Now, and a sub n is this function of n. Okay, remember the function, when we're looking at sequences, if you can express the sequence by its rule as a function, of course, for a sequence, n is always an integer, generally a positive integer. Okay? F would be a continuous function of any variable, but if you put the n in there, if that defines your a sub n, then that is your function. You could put an x in there, and that would make it continuous, but we're only interested in that part. So, and that's what we'll do right here. Then the summation of n equal 1 to infinity of a sub n and the integral from 1 to infinity of f of x, not n, but f of x dx. So you only do this on continuous functions. This is supposed to be an area, and you can't do an area over just integral values, you know, don't have any continuity there. And this has to be continuous, okay? But you can take the integral. So that integral and this summation are either both converge or they both diverge. If this converges, that has to. If this diverges, that has to, you know, and vice versa, okay? So they either both converge or diverge, so that's the integral test. If you can come up with a function that defines, according to the rule of your sequence, what your a sub n is, then the summation of that sequence, which is your series of a sub n, will be what the integral of your f of x is. All right. All right. Now, this is fairly easy to do just on its own without using the integral test. But if you are going to use the integral test, the function, that would be x over x squared plus 1, right? So the function would be f of x is x over x squared plus 1. It's positive. It's continuous for x greater than or equal to 1, for sure. Certainly for x less than 0, it's not positive. Okay, so we're not going there. But it is positive for any x greater than or equal to 1. To determine whether f is decreasing, find the derivative. Okay, we know how to do that. Well, sadly, it's a quotient rule. The quotient rule says it's low d high, which is x squared plus 1 times 1, derivative of your numerator is 1, minus high d low, this times 2x, divided by low, or low squared, the denominator squared. Okay? If you work this out, this is just x squared plus 1 here, minus 2x squared. So that would be 1 minus x squared. Positive x squared here minus 2x squared would be a minus x squared. So 1 minus x squared divided by this entity. Well, that for any value greater than 1, greater than or equal to 1, 1 minus x squared is going to be negative, right? Your denominator is always positive, okay? So that means positive divided by negative is going to be negative. So your first derivative is negative, meaning it's always decreasing. So that allowed you to determine, well, yep, we met the rule so far. The function is positive. It's continuous for x greater than or equal to 1, and f is decreasing. be a minus x squared plus 1. And for any x greater than 1, that derivative is definitely less than 0. So it follows that f does satisfy the conditions for the integral test. That's all just to get the conditions right. I've got one, thank you. I may take you up on it if I use all these up. Okay. You can also integrate, I think I'll take one now, that, and that is an integrable function, right? How would you integrate that? Whoa, this is going back to the first of the term, isn't it? What rule? What technique? Would you integrate that? Oh, goodness, don't tell me we've forgotten already. We're saying about these getting out of the container. How do you integrate that? What's the most complicated part of the problem? The denominator, x squared plus 1. You let that be your u, the du would be 2x, right? And then you have an x divided by 2. So if you use substitution, and what they do is divide by 2 and multiply by 2, that's just multiplied by 1. Now you got du over u. What does that integrate to be? Integral of du over u. Log of u, ln of u. Okay? Now this is going from 1 to infinity. And when you evaluate the log at infinity, it's infinite. Log of 1, of course, is 0. So the bottom is no problem. This is the top. This gives you the 1/2 limit of log of x squared, okay, and u was x squared plus 1, so that'd be log of that. And, all right, plugging in the way they said to. He said he would be here.
Sorry I'm late.
No problem. Never can tell about those doctors, can you?
It took me 2 hours.
Yeah. To see you probably 5 minutes.
Yeah.
Yeah. When you plug in these limits, you see you don't really go, you can't evaluate it at infinity. So you substitute a b there, let b approach infinity and solve this one. When you put this in, limit of b squared plus 1 minus when x is equal to 1, b1 plus 1 is 2, log 2. Okay. Now, if you let this go to infinity, this is it's going slowly, but it's still increasing without bounds. Okay? That's going to infinity, so the series diverges. Everything worked on it fine, except that limit is a converging limit. It's a diverging limit. So that series diverges. Looked promising, but it wasn't enough. We're in section 9.3. You're not responsible for this test-wise, 191 and 192, but I wanted you to see these things, at least be exposed to us before you, because we don't have time to go over it in great depth. I'm probably doing more than I should. here's a P series and a harmonic series. I have a little blurb over here on the harmonic series going way back to Pythagoras. And he was, I think, quite musical too. They discovered a whole lot about harmonics way back then, long before you would have thought they had the tools to do so. But they did make those discoveries. Okay. Second type of series that has an arithmetic test for convergence and divergence. This is called the P series. It's the summation n equal 1 to infinity of 1 over n to the p power. Now certainly if your p was in the numerator, if your n to the p was in the numerator, no hope. That's going to take off and go. But with that in the denominator, n to the p is an increasing function as n goes from 1 to infinity, greatly increasing function, but in the denominator you would think this is going to 0. And indeed it is. But remember, just going to 0 doesn't guarantee it converges. So here's the p series. 1 over 1 to the p plus 1 over 2 to the p equals 3 over 3, 4 to the p, and so on. That's the p series, where p is a positive constant. Now, if p is equal to 1, this would be 1 over 2 plus 1 over 3 plus 1 over 4 plus 1 over 5, and so on and so on. Okay? That's the harmonic series. Okay? Now, that's the one we were looking at in the next to last example in the last section. I believe that was it. Okay? And it's very similar to the one we just looked at in the first example of this section. In a sense, you might not see that, but there is a sense that it's true. Okay? But that's our harmonic series. And P is anything else, it's no longer considered harmonic. A general harmonic series is of the form summation of 1 over 1 over parentheses a n plus 1. In other words, a linear expression, okay? 1 over n, that's a linear expression, but that's with coefficient 1 and y-intercept of 1. Slope of 1, y-intercept of 1. This allows any slope, any y-intercept. Okay. In music, strings of the same material, diameter and tension, whose lengths form a harmonic series, okay, produce harmonic tones. Okay? That's strings of the same material, that's one thing. Same diameter of material, that's another thing. And same tension on the material. All those are the same. Their lengths form whose lengths form a harmonic series, they produce harmonic tones. Any of you play guitar? Or any string instrument? Piano? Y'all intelligent. No, I'm sorry. Okay. But you've seen people tune guitars or basses or any kind of instrument like that. That's what you're doing. You're getting same material, or varying diameters, varying tension. Then the lengths. You've seen a baby grand piano, right? Part of it goes way, or a grand piano. Part of it goes way up there, and part of it is very short. The high end's down here, the bass is down here, because those lengths are similar. Now, they do other things like changing the diameter, especially in an upright piano. You can't have all those lengths, so they change the diameter, producing the same deal. Okay. So the convergence of a P series, 1 over n raised to the p power, it converges for any p greater than 1. So the harmonic series does not converge. The last one we saw, the one before that, they do not converge. But if any p greater than 1, it does converge. Even 1.000001, that will converge. But if P is equal to 1, it won't. Diverges for anything. Now, of course, P can't be negative. So you do 0. We don't want P to be 0 either, because that would just be 1 plus 1 plus 1 plus 1 plus 1. That's going to diverge too. But we don't even mess with that. And any P less than or equal to 1. Equal to 1 would be a harmonic series. Anything less than 1, greater than 0, is going to diverge as well. So that's a pretty handy tool to have in your belt when you're doing those kinds of series. Okay. Discuss the convergence or divergence of the harmonic series. What do you think? Converge or diverge? I thought I just said that about 3 or 4 times. Diverges. And the P series would P equal to?
It's
Greater than 1, so it converges. You're absolutely right. From Theorem 911 follows a harmonic series where P is equal to 1, or even if you use the AN plus B, that still acts like this, that diverges. And the P series in P is greater than, P is 2, which is greater than 1, that has to converge. Okay. 2 pretty quick ones. They have more examples in the book, but we're not going to do them. No, you're not responsible for the homework. You can do any of them you find are useful. Let's move on to 9.4. I shouldn't be taking too much time with this because we need to get on to chapter 10. And there's so many sections here in 9. All right, we're still chapter 9, infinite series. 9.4 is comparison of series. We'll use a direct comparison test to determine whether a series converges or diverges. And we'll use a limit comparison test to determine whether a series converges or diverges. So if you haven't picked up on it now, the big question with series, do they converge? Do they diverge? Okay? And unfortunately, you'll see just about everything from now on. But if it's this, you can't tell. Okay? Unfortunately, there's going to be some of those too. So 9 point, wait, I hit the wrong button. So let's do the direct comparison test. For convergence tests developed so far, the terms of the series have to be fairly simple, and the series must have special characteristics in order for convergent tests to be applied. Okay? If you think about it, everything has to be, if you're going to get a function out of it, it has to be a pretty regular type thing. Otherwise, your function gets completely wacko, and you can't tell anything about taking a group integral of it or anything else. The slight deviation, just ever so slight of a deviation from the special characteristics, can make a test completely inapplicable. It's sad but true. And guess what? Most of the time, nature is not perfectly predictable. Okay? You could have slight deviations, so maybe some of your other things you can't do. So, for example, in the pairs listed below, they say the second series, I wish they hadn't told you that, cannot be tested by the same convergent test as the first one, even though it's very, very similar. Okay, how about this one? What kind of series is this? Early, yeah. Second?
harmonic.
It's not harmonic. That would be if, no, that would be something over n, not over 2 to the n. Earlier. We talked about it in the 9.2. It was on the first series we looked at.
Geometric series?
Geometric series. The ratio is 1/2. The A, I think they call it, is 1. Okay? So that's a geometric series. We know it converges. Okay? to 1 over 1 minus 1/2. So that converges to 2. But here, what about that? Well, we can't tell. Surely this ratio, the sequence converges, but that doesn't mean that the series does. In fact, we're not even guaranteed that the sequence converges to 0. I think it does, but that still doesn't tell us about the series. So, looks a little similar, but not, okay? If that was an A, no problem, but that's an N, so that's changing too. Okay, how about this one? What kind is that? P series, does that converge or not?
No. Divergence.
Wait, no, this is greater than 1.
Oh, okay.
Yeah, so it converges. P series converges really fairly quickly too. Okay, but how about this? Wait a minute, okay? Everything in my gut tells me it should, but we can't guarantee it because it's not a P series. And the only rules we have is for the P series. I think it would converge, but we can't tell what it would converge to because even if you did a functional thing on this, that's not going to be an easy one to do either. Okay? Now, A sub n is that mess. Okay? What can you tell me about that? Sort of looks a little like this, but it's not really the same. You can divide everything by 1 over n, remember? And this becomes n plus, that goes to 0. So that A sub n certainly goes to 0 for large n. But you can integrate this because this is, again, U substitution. I couldn't think of my letter. U substitution will certainly work on that, just like it did the earlier one. So that's easily integrated. But how about this one? With the n squared up here, no, that's not easily integrated. Because even if you multiply this out, you wind up with n to the 4th, not an n cubed. N cubed would work to integrate it, but this one doesn't have an n cubed. So, no. Actually, it says easily integrated, and that may be it's not. But no, I don't even think a partial fractions is going to work on that because that's an n squared up here. But it might. The key here is not easily integrable. It may be integrable, but it's not easily integrable. Okay, Devin. Well, we now have more than half the class here, so it's good we finally got there. So, even though this is a series that's easy to tell, that's a series easy to tell, this is one we can do our change that to a function and integrate it. That's not geometric, that's not P, and that's not easily integrable. Like I said, we might be able to find out a way to integrate it, but it's not an easy process. Okay. So, there in 9.12 says, and by the way, we're in 9.4 now. You're not responsible for this on the test. You're only responsible on the test, 9.1 and 9.2, sequences and series. These parts, we don't have time to go into great detail. I'm probably doing too much detail right now, but I'm just doing this so if you ever need it in the future, hopefully you've at least seen it once and it won't come as a big shock to you. So here's a direct comparison test. Here's the key. 0 is going to be less than a sub n. In other words, a sub n and b sub n need to be positive. Okay? For all n. For all n. Okay? No negative numbers for A or B. Okay? All in. Now, B sub n is always greater than or equal to A sub n. A sub n is never 0, and B sub n is never 0. A sub n is always less than or equal to B sub n for any other value of n. Okay? A sub n always less than or equal to B sub n. Now, if the summation of n equal 1 to infinity of B sub n does converge, if somehow we knew that, if that's one of the ones we can do a test on and can tell it, and the fact that A sub n is always less than or equal to B sub n, then we know this one has to converge too. Because if you're adding smaller numbers or the same numbers together and this converges, that one's got to converge. If every term is less than or equal to the ones here, and that converges, it's got to. Now, if A sub n, this one diverges, then B sub n diverges. So if we know something about this one, and we know that B sub n is always greater than or equal to A sub n, and that diverges, no way that was going to converge. It's got to diverge as well. Now, can't you sort of smell the uncertain thing here? Okay. If B sub n I'll let them get to it in a minute. You'll see there is a thing that you're uncertain about. Okay. Now, this one is not, I'm trying to do it quickly. If this was in there, what kind of expression would this be? What kind of series would that be? Second? Geometric. That would be a geometric series. And those converge, right? Now, because that's a geometric series, if you make the denominator a little bigger, that makes these things smaller, the fraction smaller, right? 1 over 9 is less than 1 over 7. 1 over 33 is less than 1 over 31, right? Okay? Because anytime you make your denominator bigger, it makes the overall expression smaller. Well, if then the B sub n term, the A sub n term is always less than your B sub n, if the B sub n converges, then this one will converge as well. And that's what we see here. That series that resembles, looks a lot like this one, just without the 2 in front. And we know this one is a convergent geometric series. Then term-by-term comparison tells you that for every term, this term is less than that because the denominator is 2 more than that. Okay? But this one converges to this one's got to converge. So, what it converges to? No clue on, well, yeah, for n going to infinity, it's got to basically converge to the same value. So by direct comparison test, this given series converges. That one converges. Okay, now, yes. Oh, okay, just stretching. Okay. I'm sorry, I did say it wrong before. The conclusion is supported by this figure, which shows the sequence of the partial sums of A sub n, which we were trying to figure out about in this one. So yeah, these are the sequence of partial sums, and it is a different number. It doesn't converge to the same number. We know what number this converges to. That's a geometric series. This one, you just know it's something less than that. You do know it converges, but what value? That's not completely, well, let's see. That would take some effort to try to do. Okay. That was direct comparison test. Let's skip on over to limit comparison test. Sometimes a series closely resembles a p-series, okay, or a geometric series, we've seen that, yet you cannot establish the term-by-term comparison necessary to apply the direct comparison test. Under those circumstances, you may be able to apply a second comparison test, which is a limit comparison test. And here's what this has. It's going to sound maybe a little similar, but it's got some subtle differences. If A sub n is greater than 0, okay, remember that was required before, and B sub n is greater than 0. They can't go negative. Okay, both of those are greater than 0 for all values of n. Now, the limit is n, and here's the other condition. The limit as n approaches infinity of A sub n over B sub n does exist. Okay, so A sub n can't be enormously larger than B sub n and getting larger. Okay, it may be larger, but the ratio exists. Okay, where L is finite and positive. Okay, then the limit, the summation of A sub n equal 1 to infinity, and the summation of B sub n equal 1 to infinity, either both converge or they both diverge. Okay, so if you know something about one, and I was trying to figure out what new test this was. Back when I learned this, it's called the ratio test, not the limit comparison test, though that certainly works too. But I always call this the ratio test. I think you'll see that in some text. Okay, so show that the general harmonic series diverges. Okay, well that was based on what we did before. You basically show that you know that the 1 over n diverges, P test, but you just make the comparison with this. So we know this one diverges because this is a divergent harmonic series. We knew that from before. So let's do the ratio of these two. Okay? Now, which do you put on top? That's the question. Okay? They put this one on top. Okay? And with A greater than or equal to 0, in other words, your slope is positive and your B is positive, then I think that almost guarantees you this has to be greater than that. Okay? But let's see. Let's do the math here. Well, 1 over the ratio, 1 over the ratio, that is the ratio of the denominators. Because to do this divided by this, you invert this one and multiply, so that puts that on top. So now I think you see it really doesn't matter, because to evaluate this one, divide this by n, and that by n, and that by n, everything by n. Okay, this will give you 1 over A plus something going to 0. Well, your limit of that is 1 over A. Now remember, A is some positive number, not an infinite number or anything else. It's a positive number. And what was the rule? The rule said if that limit is L is the limit is finite and positive, we just determined the limit was 1 over A, which is what we said. I'm sorry. Because that limit is greater than 0, you can conclude from the limit comparison test. Remember, that is what we were doing. Sorry. That limit is not 0, okay? And that's the key. It's greater than 0, then the series diverges. I just don't think, sorry, I think they explained that one all that well, but that's what they get me. So the limit comparison test works well for comparing messy, weasel word there, messy algebraic series with a P series. And choosing an appropriate P series, you must choose one with an nth term of the same magnitude of the nth term of the given sequence, given series. So this you will compare to 1 over n squared. Yeah. This one 1 over n to the 1/2. Okay. This one 1 over n to the third. Okay. All right. This was the sort of tricky one here. Who cares? As n is going to infinity, the 2 gets less and less important, right? 3 times an enormously large number minus 2 is still going to be an enormously large number, much closer to this than that. It doesn't matter whether you add or subtract a little number from it, or even a big number from it. N is going to get enormously large, going to infinity. This dominates. So remember back in pre-calculus algebra, if you had me for it, you probably remember I focused on ratio of leading terms. And that's exactly what you do here. This acts as 1 over 3 to the 3 times n squared. Forget about the 3. The n is going to take over, so it's 1 over n squared. This is ratio of 1 over the square root of 3 to n. Well, the 3 isn't going to matter too much. 1 over the square root of n. So that's 1. Yeah, that's 1. This is n to the 1/2 then. And this will be ratio of leading terms. I'll act like 1 over n cubed. P series, that would converge. P series, this one will not. P series, that one will converge. Okay? And if the comparison works, then they both either converge or diverge. And that's what they said this. The ratio is just some number, 1 over a. So it's not, and the ratio has to be positive, and this is positive. That's all the a tells you, it's positive. But it's a numerical comparison to this. This one diverges, so therefore this one's got to diverge too, because the ratio is just a constant. And if one diverges, the other does. Okay. I'm sorry, that. No homework. Ooh. Oh, yeah. So let's move on to 9.5. How are we doing on time? 3 minutes. Let's get as much of 9.5 done as we can. Since there's no homework exercises here, we'll do this. Okay? Again, infinite series. Again, I'm sorry about my coughing. That's really taking up too much class time. 9.5 is alternating series. Up to now, we've had, remember, the A and the B both have to be positive. So we use alternating series test to determine whether an infinite series converges. Alternating series remainder to approximate the sum of an alternating series. Classify a convergent series as absolutely or conditionally convergent. Okay, and rearrange infinite series to obtain a different sum. Okay. All right, let's try it. The simplest series that contains both positive and negative terms is an alternating series. Okay. I don't know why they say simplest series. Any series that contains, well, I'm sorry. Yeah, this, okay, I got what they're saying. The simplest series that contains both positive and negative terms is one that alternate every term. The terms alternate in sign. So here is minus 1/2 to the n. Okay? This is a series, n equals 0 to infinity. So the first one, when n is equal to 0, that's going to be negative 1/2 to the 0 is, anything to the 0 is 1. Okay? Negative 1/2 to the 1 would be negative 1/2. To the second would be a positive 1/4. So you see, you can pull out into the minus 1 times raised to the nth power here, get the minus sign out here, and then you're left with this just raised to the go. Okay? Now, that is a geometric series. It's an alternating geometric series. Your ratio is now negative. So your by your rule for geometric series, it'd be your A is 1 over 1 minus R. Well, R is a negative 1, so 1 plus a 1/2, which is 3/2, so that would be 2/3. Alternating series occur in two ways. Either the odd terms are negative or the even terms are negative. One or the other, and the other are not. Okay. How are we now? Out?
Yes, sir.
Second? Okay. So, next time, we didn't get very far here, but next time we'll begin with Theorem 9.14. Okay? No new homework exercises there. There were from what we did before. But again, 9.5, which is a sort of a long one. 9.6, there's your ratio test. So maybe I was wrong. 9.7, that's a long one too. Very long. 9.8, this is a long chapter. 9.9, and I think 9.10. I think that's the last one. Yeah. Just a slideshow. Then we'll get going in chapter